Hey everyone, welcome to week 6 of General Chemistry. I am your mom, Marian Pine, your lecturer for this week. Our topic for this week will be all about the 5 gas laws, namely the Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, and Avogadro's law. But before we proceed to the first gas law, let us first try to answer how are gases different from solids and liquids. So you've been studying since junior high school the differences of solids, liquids, and gases. Now let us also try to enumerate the different characteristics of gases. First, gases have no definite shape and volume. As seen on the picture, if you are to compare solid, liquid, and a gas, solids have definite shape and they also have a definite volume. Liquids do not have a definite shape because they follow the shape of their container, but they have a definite volume. Gases do not have a definite shape and they also do not have a definite volume because they randomly move. The second characteristics of gases is that particles of gases are in constant random straight line motion and they have elastic collisions. As you can see on the animated picture in here, these are gas particles moving in random and straight lines only. And they have elastic collisions. So in your physics, elastic collision happens when two objects collide with each other and then they immediately separate. They do not stick together. So that is the movement of the particles of gases. They collide, but it's elastically. They immediately separate. The third characteristic is that they have an average kinetic energy directly related to Kelvin temperature. So, meaning to say, kinetic energy is directly related to temperature. And basically, we define kinetic energy as the energy in motion. So, meaning to say, as the temperature increases, the kinetic energy of the gas particles also increases. So as you can see on the two illustrations on your right-hand portion, the first illustration shows the gas particles is contained in a cooler environment. The arrows represent the movement of the gas particles. It is shorter, meaning to say they are less energetic. They do not move energetically compared when they are in a hotter environment or in a higher temperature environment. So the hotter it is, the more energetic or the more excited the particles of the gas move. And so the higher is the collision. So since gas particles, being in a constant random motion, collide with one another and with the surface they are contained in, the force therefore produced when these particles collide with the surface creates pressure. And pressure, which along with temperature and volume, is an important property of gas. So in gas laws, we are actually studying the relationship of these three variables: the pressure, the volume, and the temperature. So I have in here some common units for pressure, temperature, and volume that we will be encountering in problem solving later on. So for pressure, we have torr, we have mmHg or millimeters of mercury. We also have atm or atmospheres. We also have Pascal, and we also have PSI or per square inch. And I also included in here simple conversion for pressure units. That 1 torr is equivalent to 1 millimeters of mercury and 1 atmosphere is equal to 760 millimeters of mercury. For temperature, we have three common units. We have Kelvin, we have degrees Fahrenheit, and degrees Celsius. But please remember that the standard unit for temperature for gas laws will be in kelvins. So if the problems later on, the temperatures in the problems later on are expressed in degrees Fahrenheit or in degrees Celsius, we need to convert it first to kelvins before we could solve the problem. And we have here the conversion formula for temperature. For volume, I listed 3 common units. We have the cubic decimeter, we also have liter and milliliters. Now we also have this what we call standard temperature and pressure. The standard temperature and pressure is a set of conditions for experimental measurements to be established to allow comparisons to be made between different sets of data. Since temperature and pressure vary from place to place, scientists have decided to use a standard reference point, and that is now our STP in calculations and equations. So as you can observe in here, the standard temperature is at 0 degrees Celsius, the freezing point of water, which happens to be that the equivalence of 0 degrees Celsius is 273 kelvins. For the standard pressure, that is equivalent to 1 atm or 1 atmosphere. This is the pressure exerted by the atmosphere on Earth at sea level. And as mentioned earlier, 1 atm is equivalent to 760 millimeters mercury, or it's also equivalent to 101.3 kilopascals. So let us now proceed to the different gas laws. First is Boyle's law, named after Robert Boyle. So what does the Boyle's law states? The Boyle's law states that at constant temperature, the volume of a gas is inversely proportional with pressure. So Boyle's law is studying the volume-pressure relationship, and it's inversely proportional. So mathematically, volume is inversely proportional to pressure. So that's 1 over P. Introducing now our constant represented by small letter k. Our constant is temperature. Changing the proportionality symbol into equal sign, that will become V is equal to 1 over P times the K. So 1 times K, that's K. And solving now for constant K, you just have to simply cross multiply so that K is equal to V times P. Okay, so in gas laws, we are actually considering initial and final conditions. So if that is the case, if we have initial and final conditions, the final formula for Boyle's law therefore is P1V1 is equal to P2V2. So again, it says in here that volume is inversely proportional to pressure. That means to say, when you increase the pressure, the volume decreases. Or if you increase the volume, the pressure decreases. So let's try to take this animated picture as an example. So we have here a pressure reader and a container with a piece of wood. Okay, so as you can see, as you press it down, the volume is decreasing. So from this volume, as you press it, it decreases the volume up to this point. And if you are going to look at the pressure reader, as you press it down or as you push it down, the pressure increases. So it clearly manifests that decreasing the volume will increase the pressure. Why? Because decreasing the volume of the container forces the gas particles in here to collide more often. And if they collide more often, the pressure therefore increases. Okay? But as you try to pull it back, or you try to increase the volume, say you pull this block upward. So increasing the amount of space available will allow the gas particles to spread farther apart. And if they are spread farther apart, reduces the number of particles available to collide with the container or with one another. And so, the pressure decreases. Let's take this situation also. So we have here two syringes with movable pistons. So here is the piston. Here is also the piston. It could be moved up and down. For the first syringe, the volume is at 100 ml at 25 degrees Celsius. For the second syringe, the volume was decreased by half. It became 50 milliliters only at still 25 degrees Celsius because again, Boyle's law, the constant is temperature. So the question is, in which system is the pressure higher, or in which has the greater number of collisions with the walls and with each other? So clearly, the answer is on letter B. Why again? Because the lesser or the smaller the volume, the higher the pressure, because it's more often that the particles of the gas collide with each other. To apply the formula for Boyle's law, we try to solve this example. A sample of methane gas is kept in 15-liter container under a pressure of 740 millimeters of mercury at 20 degrees Celsius. How much pressure must be exerted on the gas to reduce its volume to 12 liters without changing the temperature? Again, the temperature is the constant in here. So, in solving gas laws for Boyle's law, we must have four given values. We have two values for the pressure, the initial and the final, and two values for the volume, the initial and the final condition. So again, just like what we are doing on our previous topics, the first step is to write the given values. So how are you going to determine if this given value is the initial condition or the final condition? Of course, you need to analyze the problem carefully. Some problems will not state directly that, for example, some problems will not say that 15 liters is the initial volume for this sample, or they will not say that 20 degrees Celsius is the initial temperature of this gas. So, sometimes the best way to analyze problems like this, or to determine the initial and final conditions, is that sometimes the values that are first mentioned in the problem are the initial conditions, and the last or the latter values that are mentioned in the problem are the final conditions. So in this case, if 15 liters is the first value mentioned in the problem, meaning to say it's the first condition for volume. So we try to write the given. Our first pressure is 740 millimeters of mercury. Our first volume is 15 liters. The unknown is the final pressure, because as you can analyze on the problem, how much pressure must be exerted on the gas. So that's the final pressure. And then for the final volume, that is 12 liters. So using now the formula, P1V1 is equal to P2V2. P2 is the unknown. We plug in the given values. P1 is 740 millimeters mercury times V1, which is 12 liters, is equal to the unknown times 12 liters, the final volume. To solve for P2, we need to divide both sides by 12 liters. And then you cancel similar units on the left side, and then cancel 12 liters on the right side to make P2 the remaining value. So 740 times 15 divided by 12 is equal to 925 millimeters of mercury. Again, Boyle's law states that pressure and volume are inversely proportional. So as we can see here on the volume, it's from 15 to 12 liters. So there is a decrease in volume. So we expect therefore that the pressure must increase. Okay, so since the initial condition for pressure is 740 and what we solved was 925 millimeters mercury. So from 740 to 925, it increased. Okay, so our answer is therefore correct because there is a decrease in volume. Therefore, there must be an increase in pressure. Our next gas law is Charles' law, named after Jacques Charles. And Charles' law states that at constant pressure, the volume of a fixed quantity of gas is directly proportional to the absolute temperature. So, the relationship of volume and temperature is found in this gas law. The constant is pressure. So again, mathematically, we write it as volume is directly proportional this time to temperature. And introducing our constant K, which is the pressure. So V therefore is equal to T times the constant K. So if we are to solve K in here, we just have to simply divide both sides by T. So that T will be cancelled in here. K now is equal to V over T. And just like the Boyle's law, we are also considering initial and final conditions. Therefore, the final formula for Charles' law is V1 over T1 is equal to V2 over T2. Since volume is directly proportional to temperature, meaning to say, if we try to increase the volume, for example, the temperature will also increase. That's why the graph is like this. Or if we try to decrease the volume, the temperature will also decrease. So let's take a look at this animated illustration. Let's assume that the candle is not yet here or it's not yet lighted. Therefore, the temperature is still low. So when you try to light the candle, you increase the temperature. And as the temperature increases, as you can observe, the balloon starts to expand. And if you try to increase more and more of the temperature, the balloon will continuously expand. And as mentioned on the characteristics of gases a while ago, temperature is directly proportional to kinetic energy. Okay, so the hotter it is, the more excited the gas particles, and so they continuously expand. And the expansion manifests that the volume is also increasing. So the higher the temperature, the greater the volume will expand. Okay, so if this heat is continuously increasing, the balloon will end up bursting. Okay, so we also have here two situations. On situation letter A, the temperature is half. Let's say this is 50 degrees Celsius. At 50 degrees Celsius, the volume is like this. It's half the container. On letter B, the temperature was increased. Let's say it was increased to 100 degrees Celsius. As you can observe, the volume is like this. It was doubled. So the question is, in which system do the gas molecules have the highest average kinetic energy? Is it on letter A or on letter B? So clearly, the answer is letter B. Why again? Because the higher the temperature, the more excited the gas particles are, and so the kinetic energy is higher. So the answer is letter B. Applying now our formula, let's try to answer this Charles' law problem. A gas sample occupies a volume of 12 liters at 25 degrees Celsius and 750 torr. At what temperature will the gas occupy a volume of 15 liters at 750 torr? So we have here volume expressed in liters. We also have here a temperature. We also have here pressure. Now take note in Charles' law, the constant variable is pressure. So don't be confused on this. The unit or the value for pressure will not be needed in solving the problem because it was held constant. So only pressure, only temperature and volume. So we write now the given. We have initial volume, that is 12 liters. For the initial temperature, it's equal to 25 degrees Celsius. If you can still remember, I've mentioned a while ago that the standard unit for temperature must be in kelvins. So we need to convert this temperature into kelvins first. And when you convert degrees Celsius to kelvins, you just need to add 273 in here. Okay, so 25 times plus 273, I should say, will give you 298 kelvins. So this will be the unit, the value that we are going to use. The final volume is 15 liters and the unknown is the temperature, because at what temperature will the gas occupy a volume of 15 liters at 750 torr? So that is the unknown. Using now the formula, V1 over T1 is equal to V2 over the unknown T2. Plug in the given. Our V1 is 12 liters equals our V2 is 15 liters all over our T1, that is 298 kelvins, and our T2 is unknown. So if you are going to solve for T2, just simply cross multiply. So that T2 times 12 liters is equal to 298 kelvins times 15 liters. So to solve for T2, divide both sides by 12 liters. So cancel 12 liters on the left side and cancel same units on the right side. So get your calculator. 298 times 15 divided by 12. The answer is 372.5 kelvins. So again, volume and temperature in Charles' law is directly proportional. So let's check. The volume in here is from 12 to 15 degrees Celsius, liters, I should say. So there is an increase in volume. So we expect that there will also be an increase in temperature. So from 298 to 372.5 kelvins, that is an increase. So it's already correct. The third gas law is called the Gay-Lussac's law, named after Joseph Louis Gay-Lussac. So Gay-Lussac's law states that at constant volume, the pressure of a fixed amount of gas is directly proportional to its absolute temperature. So in Gay-Lussac's law, the two variables that we are investigating is the pressure and temperature. And it says in here that they are directly proportional. So pressure is directly proportional to temperature at constant volume, constant K. Okay, so P now is equal to T times the constant volume represented by K. And then solving for K, we just need to divide both sides by T. And then cancel the temperature in here so that K is equal to P over T. And again, just like the previous gas laws, we also have the initial and final conditions. Therefore, the final formula for Gay-Lussac's law is P1 over T1 is equal to P2 over T2. Since they are directly proportional, when you increase the temperature, there is also an increase in pressure. Or if you decrease the pressure, there is also a decrease in temperature. So take a look at this GIF. At first, let's assume that there is no heat yet. Okay? As you can see, the pressure a while back, the pressure reader a while back is not moving. But when you light the candle in here or this lamp, when you light the lamp, it increases the temperature. And as you can observe, the gas particles started moving in random motion. And as you heat it up more, they become more and more energetic. And so the pressure increases. Let's try this example. A helium gas placed outside a laboratory has a pressure of 5 atmospheres at 25 degrees Celsius. How much will the increase be at noontime when the temperature reaches 32 degrees Celsius? So we have here 5 atm. We also have temperature. So the unknown is the final pressure. So we write the given. For the initial pressure, that is equal to 5 atm. Initial temperature is 25 degrees Celsius. Again, we need to convert this into kelvins, so we add 273. So 25 plus 273 is equal to 298 kelvins. And then, our initial pressure is the unknown, and the final temperature is 32 degrees. Again, plus 273 to convert it to kelvins. So 273 plus 32 will give you 305 kelvins. Okay, using now the formula, P1 over T1 is equal to P2 over T2. So P2 is the unknown. Plug in the given. Our initial pressure is 5 atm over T1, which is 298 K. P2 is the unknown over T2, that is equal to 305 kelvins. To solve for P2, again, simply cross-multiply so that P2 times 298 kelvins is equal to 5 atmospheres times 305 kelvins. To solve for P2, divide both sides by 298 kelvins and then cancel on the left side. On the right side, you cancel similar units, which is the Kelvin. So 5 atm times 305 kelvins divided by 298 kelvins, the answer will be 5.12 atmospheres. Again, pressure and temperature are inversely proportional. Let's check. The temperature is from 298 to 305. So there is an increase in temperature. So there must also be an increase in pressure. So it's initially 5 atm, then became 5.12 atm. So it really increased. So this one is correct. Okay, to remember which constants go with each law, because there is a constant variable with each gas law, I have here a mnemonics for you to easily remember. For Boyle's law, since the temperature is constant, just remember the mnemonic Boyle-Tage. Letter B, Boyle for Boyle's law, Tage, letter T. Temperature is constant. For Charles' law, since pressure is constant, you just have to remember Char-Paul. Char-Paul C for Charles' law. Paul, letter P, pressure is constant. And for Gay-Lussac's law, since volume is the constant, you just have to remember Gay voice. Gay for Gay-Lussac, V, voice for volume is the constant. So if you already know the constant of each law, then you can easily memorize the formula already. Okay, so previously we have examined the relationships between any two of the variables, right? May it be a pressure-volume relationship, volume-temperature relationship, or pressure-temperature relationship. However, situations arise where all these three variables change. That's why they came up with this combined gas law. So as the name suggests, combined gas law is the combination of the previous gas laws. So it expresses, therefore, the relationship of pressure, volume, and temperature of a fixed amount of gas. So for combined gas law, only the amount of gas is held constant. So if that is the case, putting all together the gas laws, we have here P1V1 over T1 is equal to P2V2 over T2 as the general formula for this gas law. So let's try to solve this example. 3 liters of the gas at 29 degrees Celsius and 0.75 atm is brought to standard temperature and pressure. What will be the new gas volume? So we have already here the initial volume, the initial temperature, and the initial pressure. The unknown is the final volume. So where are we going to get the final temperature and the final pressure? So we write the given. Initial pressure is 0.75 atmospheres. Initial volume is the 3 liters. Initial temperature is the 29 degrees Celsius. Convert this first to kelvins. So that will be plus 273. So 29 plus 273 is 302. Kelvins. And then for final pressure, it's 1 atm. Where does this 1 atm came from? Again, it says in the problem that it was brought to standard temperature and pressure, or the STP that I have shown you a while back. Why do we use 1 atm and not 760 millimeters mercury? Because from the previous given, or from the initial condition of the pressure, it was expressed in atm. That's why we also need to use the standard pressure at atm. So that is equal to 1. And then for the final volume, that is the unknown, and the final temperature is 273 kelvins. Again, why not the 0 degrees Celsius? Because Kelvin is the standard unit and 0 degrees Celsius is just equivalent to 273 kelvins at standard temperature. So using now the formula, P1V1 over T1 is equal to P2V2 over T2. V2 is the unknown. So plug in the given. Our P1 is 0.75 times our V1, which is 3 liters, over our T1, which is 302 kelvins. Our P2 is 1 atm, V2 is the unknown, divided by our T2, which is 273 kelvins. So to solve for V2, simply cross multiply. So that will become V2 times 180 M times 302 kelvins is equal to 0.75 times 3 liters times 273 kelvins. And then solve for V2, divide both sides by 180 M and 302 kelvins. And then cancel 180 M and 302 on the left side, and cancel similar units on the right side. So bring out your calculator. 0.75 times 3 times 273 divided by the product of 302 and 1. So the answer is 2.03 liters. So you just have to rearrange the formula in order to get the unknown. So gas law problems actually are easy to solve. You just have to rearrange the formula so that you could get the unknown value. Okay. The last one will be the Avogadro's law, named after Amedeo Avogadro. For Avogadro's law, Avogadro stated that two gases that occupy equal volumes under the same temperature and pressure contain the same number of moles. So in Avogadro's law, we have a new variable in here because we are actually looking into the relationship of volume and the number of moles. And as Avogadro stated that they are equal under constant temperature and pressure. So if that is the case, if we try to change the volume, for example, we try to increase the volume or the container where the gas is contained in, the number of moles also increases. So let's take this illustration. Okay, initially, when you do not pull the piston yet, the volume is small. And so the amount of or the number of moles is also small. But as you increase the volume, if you pull the plunger in here, or the piston I should say, as you can see, there are also more number of moles entering the container. So really, there is a direct proportionality between volume and number of moles, regardless of the nature of the gas. So, for example, on this situation, you put in here either nitrogen gas, hydrogen gas, or helium. It will always be the same because it's regardless of the nature of the gas. So therefore, the formula for Avogadro's law, since they are directly proportional, considering two conditions, the initial and the final, V1 over N1 is equal to V2 over N2. So let's try to solve this problem. A sample with 3 grams of helium has a volume of 2.25 liters. What is the volume if the sample is increased to 1.2 moles? So the unknown in here is the final volume. So we write the given values. Our initial volume is 2.25 liters. Our initial number of moles, as you can observe, it's expressed in grams. There are 3 grams of helium. And we already learned on our previous topics how to convert grams to moles. Okay, so we need to convert these 3 grams first into moles so that we could use the unit or the value in solving. And then, of course, the final volume is the unknown, like what we've said. And the final number of moles is 1.2. So, we convert first the 3 grams of helium into moles. And when we convert grams to moles, you just have to simply multiply it with its equivalence to 1 mole. 1 mole of that element over its atomic mass. So the given is 3 grams helium times, okay, in every 1 mole of helium, there are 4 grams of it. This must be helium, He. Okay, so where did this 4 grams came from? It is the atomic mass of helium. This is found on your periodic table. So just simply divide 3 grams divided by 4 grams, or 3 times 1 divided by 4. So that will be equal to 0.75 moles. 0.75 moles of helium. So we are now ready to solve for the final volume using the formula. So V1 over N1 is equal to V2 over N2. V1 is 2.25 liters over N1, which is 0.75 moles, equals V2 is the unknown over 1.2 moles. And then to solve for V2, cross multiply, so that will become V2 times 0.75 moles is equal to 2.25 liters times 1.2 moles. Solving for V2, just simply divide both sides by 0.75 moles and then cancel. And then cancel similar units on the right side. So on your calculator, 2.25 times 1.2 divided by 0.75, that will be equal to 3.6 liters. So let's check if they are truly directly proportional. Okay, the initial number of moles is 0.75. From 0.75 moles to 1.2 moles. So there is an increase in the number of moles. So also, there should also be an increase in volume. So it's from 2.25 to 3.6. Okay, so it increases. So that's already correct. So that ends now our discussion for this week. I hope you learned how to solve problems regarding gas laws. So it's just very easy because they are all formula based. You just have to rearrange the formulas in order for you to get the unknown value. So thank you for watching, and be updated on science videos in senior high school by visiting Science Saya. There are available videos in YouTube. So I would like to end my presentation with this quotation. Life is a pressure cooker, and whether you remain serene or become stressed out depends on how you handle that pressure. Thank you once again, and good day.